Что-нибудь слышно? Или нет?
Да, слышно.
Yeah, so I hope today we will finally finish this. You see that it is our third time we try to solve certain problem, namely maybe you remember this problem. So we fix some rational rational number q. Well, assume it's not well. Maybe even an integer which is not 0 or 1, and we assume that it is square free. And the question is whether there exists a cyclic extension of the rational numbers containing cyclic extension of Q of degree 4 containing square root of Q. Containing square root of Q. So you see, we try to solve this problem by iterations. Yeah. So the first time, sorry.
So, and is there should there be a condition of the Galois group being Zeeman 4, not Zeeman 2 square?
Yes, that's the question. Yeah. So so we want.
So we can rephrase it like the cyclic extension with Galois group Zeeman 4.
Yes. This is the same condition. The same condition as cyclic as a Galois extension with a cyclic Galois group of order 4. Yeah. So so what we already know, we know that of course this Q should be positive, yeah, because otherwise we have. But actually, we are going to do this without even this condition. So actually, let's try to solve this. Let's try to solve this. So first of all, my first question is So we have maybe I should give a name. To this extension, let us call this L of Q containing square root of Q. Yeah, so we have this L, we have something in between probably and Q. Yeah, so we have this is Q of square root of small q, and you see that so this we want to be a Zeeman 4 extension. And this one is again. So what can you say about the upper extension? This one. What kind of extension should it be?
Degree 2.
Yes, that's right. Of degree 2. So what could be this L? Do you know what is the general form of any degree 2 extension?
Square root of some element.
Yeah, so that's right. So this should be square root of yes. Formally speaking, we should extend this field. Yeah, so this will be q and the square root of something like a plus b square root of q, where a and b are certain rational numbers. Yeah. But what can you say? What can you say?
Square root of q can be
Omitted. Yeah, you want to say? Yes, that's a good point. But let us. Yes, you're right because.
it's also alpha square minus I over v.
Yes, so let us denote this by alpha, yeah? So you can omit this, yeah, because square root of q is, well, depends. We should be a little bit careful because then we have to say why b, this can be omitted if b is non-zero, yeah?
We discussed it and got to the point where b should not be zero.
Yeah, okay, so let us fix this on the blackboard, just to say that square root of q is just it can be expressed in this in terms of alpha, but let us say why b is not zero. Why? Because otherwise, if b is zero, then
You mean Galois group is Z2 was multiplied by Z2.
well,
Square root of a and square root of
it is.
If they doesn't coincide with square root of
Yes, but in any case, the Galois group of this field is of period 2. Even you see that in principle A may be 0, A may be 1,
Okay.
A may be equal to B, but anyway, this since the Galois.
well, it's square root of q, not b. Because we assume that b is zero.
Ah, thank you. Yes, yes, yes. Since this. Since the Galois group of is of period 2. So it is annihilated by multiplication by 2. Okay, so yeah, okay, now we want this field to be a Galois extension. Yeah, so now that b is non-zero, we want this, so L over Q is Galois. And therefore it contains square root of the conjugate, yeah, of the conjugate of alpha. Let's call it beta. L. What else? And then it contains. You see that it contains the product, yeah, of alpha and beta. So what can you say about the product? So it contains
Square root of a square minus b square.
q b square, yeah. Okay, so it is L. It is an L. But so you see that what is this? This is again a quadratic element. Yeah, so we can put it somewhere here. So it is alpha beta. Yeah, so it is in a subfield in L, and so the question is, what can you say about this extension?
So it should be Q, or Q is square root of Q. Small. I mean, there is only one extension in L because of Galois group.
It's, yeah, it's cyclic, yeah. It is cyclic, so there is only one intermediate subfield of any given degree. Yeah. So yes. So this means that we have two options that either square root of a square q b square is rational, or square root of a square minus q b square belongs to, well, of course this this is more looks a bit stupid in the sense that maybe belongs to this one, yeah?
Mm-hmm.
Why should these extensions coincide?
You see that this group is cyclic, and this means that there is only one intermediate subfield of each degree over Q, or over which L is of a given degree. Yeah. So it's, so the options are that it is either this field or this one. So yeah. So in the case that it is not rational, then it belongs to this field, but it is not rational. Yeah. So we assume that it is not rational. Okay. And the question is whether this element can be rational.
And this, so we can see that it's q is square for E.
Yes.
And
Yeah. So, but you see that actually that's what we have discussed in our first attempt to solve this problem. So there was an argument with a discriminant. So what is the discriminant? Discriminant of the minimal polynomial of alpha. So
it's non-zero, so
no, no. You see, it is always non-zero because our extension is separable. Yeah. So what is the minimal polynomial of alpha? It is, well. It doesn't matter what it is, but it does matter what are its roots. Its roots are alpha, minus alpha, beta, and minus beta. Yeah. So then the discriminant. Well, maybe I should write this just to be complete. It should be x squared minus a square minus b square q. Yeah. Okay. So the discriminant is what is discriminant? It is we consider all differences to alpha minus beta times alpha plus beta, so it will be alpha square minus beta square. Next, minus alpha minus beta times minus alpha plus beta, so it will be square. And times twice beta. Yeah, so it will be 4 alpha beta and everything square. Yeah. So what is this? So what is this? This is so what is this? This is 4 alpha beta. What is alpha square minus beta square is what is alpha beta? Yeah, it is twice b square root of q square and square. Okay, so you see that so the question is whether d is a square. Whether d is a square.
let's dispose of
yeah, so this maybe we should write this as 16 b, alpha beta q b square.
B squared.
Yeah. So you see that actually the question is whether this is a rational number. So and this is alpha beta is precisely this element.
And rhetorically,
And but what does this say to us? Whether this so the choice is that if
what happens if D is a square?
if D is a square, then our Galois group should consist of even permutations. But in our case, you see that we have a permutation of 4 elements. Cyclic permutation of 4 elements is not even. And therefore, this product should not be a rational number. So, and therefore, so we exclude this case because since this 1, 2, 3, 4 is odd.
And what's in this group? Why do we exclude?
Because you see, we want this group to contain an odd permutation.
So why does it contain the odd permutation?
Because it is, you see that there are 4 elements, and the group is cyclic. So it is, so the group is a cyclic permutation of 4 elements. And the cyclic permutation of 4 elements is odd. So, yeah, so we exclude this case, and therefore square root of, well, this alpha beta is an element in this quadratic extension, which is irrational. But now we have to, I have to ask you, do you remember what is Kummer theory?
We did discuss it, but
Okay, let me remind you. So the Kummer theory. Kummer theory. It says that there is, so we assume that, so what do we assume? What do we assume? We assume that, so we fix some integer, an integer. We assume that k contains some primitive nth roots of unity, nth root of unity, and then the claim is that there is a bijection between between what? Between n
there must be also L, that is some sub-extension of K.
well,
Well, we had like K intersect L nth powers of L in verticals modulo K verticals nth powers is isomorphic to homomorphisms of G and N.
Okay. But well, then we just let me just state it slightly differently, just to not to repeat literally what we have already discussed. So what could we do? We can consider just all subgroups of the multiplicative group of K modulo nth powers of K, and on the other side we consider n periodic extensions of K. N periodic means that Galois extensions with maybe abelian with Galois groups of period n, groups of period n. Yeah, so means that they are annihilated by n. And so how does it work? You just take here a subgroup and adjoin to your field all nth roots of elements in this subgroup. Yeah, so you just consider all alpha such that alpha to the n is belongs to H. Alpha to the n modulo nth powers belongs to the H. Like this. Okay, so what does this? So now our case is n equals to 2. So n is 2. So we consider. You see, we consider extension of degree 2, and we know that they coincide. What does this mean? You see that here we adjoin square root of q, and here we adjoin square root of a square minus q b square.
So you're saying that subgroup should coincide?
Yes. Yes. So what does this mean? So where is this subgroup? Here, here, and here.
Why does n equal 2 in our case? Because
Sorry?
N equals 2 in our case because
we consider quadratic extensions,
Mm-hmm.
two periodic extensions. Yeah.
Subgroup we should take subgroup generated by
Q, yes.
by Q modulo
Squares. Yeah.
squares.
Yeah.
Yes, and the second one generated by R minus
Yeah.
Q.
Okay. And what does this mean? What does it mean that they coincide?
That элемент по модулю квадрата.
Yes. Yes, they coincide modulo squares. Yeah. Yes. So this means that they are the same. These elements are the same modulo the square. So a square minus q b square over q is a square. Okay. So let's call this c square Okay, and then we get an equation a square. Well, maybe let me write more letters. Let us.
Why why does this alpha beta square or q is a square? Why is this a square?
You see that this element and the square root of alpha beta and the square root of q define the same extensions. Yeah. So
Yeah,
square root of a square minus q bit square and q define the same extensions, and this means that they generate the same subgroups here in q modulo q square. Okay, yeah. So let us denote. Yeah. So let us denote a by q x, b by y, c by z. Then we get the following equation. Yeah. So this will be q x square is equal to y square plus z square. Okay. So you see that in particular. So now we want to know whether this equation has a non-zero solution. Yeah. So what is evident here? So if there is a non-zero solution, non-zero solution, then well, first of all, q is positive. Yeah, we have already discussed this, but we can see this again. So then q is positive. Next, you see that we may assume that x, y, and z are integers. Yeah, just multiply them by common denominator. Maybe in square of this, to make sure that nothing changes when we pass to some square root. Yeah, so we can. And then one more remark that actually we see that -1 should be square modulo q, or modulo any prime divisor of q. -1 is square modulo each prime divisor modulo q or divisor modulo modulo q or modulo each prime divisor of q. You see that consider this modulo q. Yeah, wait. First of all, suppose that we may assume that x, y, and z are coprime. Yeah. Otherwise, just divide them by common multiples. So suppose that one of them is divisible by. So let us assume that p is a prime divisor of q. Yeah, and consider this modulo. So suppose that z is divisible by p. Z or y, they are in the same position. Yeah. If z is divisible by p,
then y should also be divisible by.
Yes. So then the right hand side is divisible by p square. But then the left hand side should be divisible by p square, and therefore x should be divisible by p. You see? And therefore, this means that z is not divisible by p. And therefore, it is invertible modulo p. And the y is invertible coprime. Okay, yeah, so they are y and z are invertible modulo p, and their square is 0. The sum of their squares is 0 modulo p, and therefore minus 1 is square modulo p.
So again, y and z are invertible.
Modulo p, because as we discussed, if one of them is divisible, then everything is divisible by p. And then the
sum of the
this
squares
is 0.
is divisible by q.
Yes, it is 0 modulo q, and therefore minus 1 is square modulo q, and
Y is minus 1 then square.
the sum of squares, and you can divide. So this is y square plus z square is 0. So you divide by z square, you get y over z squared is equal to minus 1. Yeah, okay, and this means that, so what this condition means? It is square modulo h prime divisor p. And therefore, well, this is equivalent to the condition that p is congruent to 1 modulo 4. So in particular, you see that we exclude not only negative rationals, but also those primes or prime factors that are congruent to minus 1 modulo 4, like 3 or 7. And
we discussed that. We did discuss that there are some conditions on p being equal to 1 modulo 4.
yes, but
Did we discuss it here? Because I remember.
Yes, we did, because we have last time we have constructed concrete examples when square root examples of cyclic extension of degree 4 containing square roots of primes of this type. So we know that it is possible to construct cyclic extensions containing square roots of these primes. Yeah? But now we say that it is not possible to construct a cyclic extension containing square root of those square free integers that do contain square roots of that do contain prime divisors or congruent to minus 1. Yeah? So this we exclude certain cases. Okay. Right, and yeah, so now we have so far we have excluded many cases, and the only thing we have to do is to construct yes. So now now the question is whether we can find such an extensions for those Q that are not that remain, yeah, after these restrictions. Yeah, and first of all, whether we can do this, and how many options do we have for that? And the answer is that actually we have lots of options for that, namely infinitely many. So what we can do, we can take first of all, yeah. So first of all, can we solve this equation? Can we solve this equation in for those q that are not they do not satisfy these conditions? Yeah. Can we?
Those two conditions.
Yeah. So now we consider. So we have excluded these cases. So now Q is a product of distinct primes. Well, distinct. It's not important, yeah, but primes congruent to 1 modulo 4. So, and the question, does this equation?
They should be different distinct.
Well,
Because we
well,
already know that Q is square free.
yes. Yes. Yeah, but even if yes, so it's not a problem. Yeah, of primes congruent to 1 modulo 4. So the question is whether does this equation has a solution?
Only in cases where y is, for example, y square is 0 modulo 4, x square is 1 modulo 4, and z square is 1 modulo 4.
No, you see that we are given some q.
Maybe,
So,
maybe we should divide by one variable and
By x square, for example.
yeah, then subtract and expand with using that minus 1 is a square.
So if I understand correctly, you claim that even
First, let's divide by x square, and then q is a sum of two squares.
is it a sum of two squares?
It's sum of two rational squares.
Well,
Yeah, but I propose to see by model some fixed prime derivative. Because we should just solve it and model each one. And
no. You see, we need. I would say we are looking for integral solutions. Integral coprime triples. Well, actually, I can ask even a stronger question, namely, is it possible to solve the following equation in Z?
it's possible because each prime divisor is modulo 1 or 1 modulo 4. No?
Yes, and then. But why? First of all, why? And
Does it have a solution in z or in z square?
well, you see, you need a pair. Yeah, maybe it's a yeah.
There is some argument which involves Gauss numbers, I mean
Yeah.
each ones.
Yes.
So we just taken we should state that no yes мы говорим, что любое число представляется рисунком двух квадратов, если там, если соответствующий идеал разваливается как бы на произведение двух, то есть там сопряженных чисел, и получается как раз и да, сейчас откуда по модулю.
Сейчас вопрос, а не зависит ли у нас от Q решения?
Зависит, конечно. То есть нам для простого числа решить, вот, а для простого сейчас почему там, по-моему, 4 было.
Yeah, actually, it's written here. You see that you can forget this condition, but you should remember this upper one. You see, we consider as you proposed, we consider the ring of integers in this quadratic field extension.
So we take in modulo P.
Yes, we consider its modulo P. And so, what are the options? The options is that it is either a field or it is not a field. Yeah, it is well, if it is either integral domain or it is not. And of course, it is not because what is this? This is the quotient of polynomials over the residue field modulo x squared plus 1. But we know that x squared plus 1 is reducible, so it is not a field. It's not a field. It's not a field. And therefore, P is not prime. So P is not prime. So P is not prime. And therefore, it is is not prime. Is not prime. And therefore, it is a product of you know that this is a Euclidean domain. So this is Euclidean domain. And therefore, so maybe z square root of 1 is a Euclidean domain. And therefore, it is a product of two a plus b square root of minus 1 times a minus b square root of minus 1. Okay.
Why there's only two multiplies?
Sorry?
I mean, why we know that Galois integers is Euclidean domain, but why there's only two reducible multiplies?
Multiples. Even why because we can look at norm. So because the norm of p is p square.
Yes.
So and therefore when you decompose it into product, then the norm of you can decompose p square as the product of norms of multiples. Yeah. So the options for the norms are only p, because if norm is 1, then it is invertible. So it is p times p. Yeah? So this means that
Okay.
okay. Well, it's not prime, and therefore it is. It can be decomposed to the product of some non-invertible elements, and they should be conjugated because the product is.
Euclidean domain is
Yeah, well, we don't use actually, we don't really need, we don't need Euclidean domain, Euclidean property itself. We need the claim that it is a principal ideal domain. So it is that there is a prime decomposition. There is a unique prime decomposition there. So, but it is evident that it is a Euclidean domain, and therefore it is a unique factorization domain. Okay. All right. Yeah. So so this is how we get that. So this means that it is just a square plus b square. And now if we have a product, you see that if we have a product, then we just can also, if the product of pi's is the product of ai plus b square root bi square root of minus 1, well, n times the same ai minus b I square root of minus 1, and so you get the product of two conjugated numbers, and this means that that it is y square plus z square for some y and z. Okay. Now, this means that that we can find such y and z, and therefore x. What is x? X, yeah, x. Yes, we're interested also in x. Okay, so far we get only. Yeah, let us check. Let us double check what have we constructed so far. So far, well, of course, maybe you see that we have excluded 0 as a value of b, so we can write q star, and yeah, so we have we can find some a b. C we don't really need, but what you see that in principle there are this equation doesn't have a unique solution, even if x, y, and z are coprime, because well, it is more or less unique for a prime, but even for a prime it's not unique in the sense that you can interchange the roles of a and b, for instance. What else? I think that's it, yeah? There are no other options. Just interchanging rows of a and b. But when you have several multiples here, you can really get something very different, because here you can switch signs. You can switch the roles of a and b, so you get some certain number of solutions, but at least a finite. You see that it is finite, but actually the point is that you can get well, dealing with extensions, you get infinitely many of them, because you see why? Because here we have taken x equals to 1, but we could take any other. So we need not to assume that they are coprime. Yeah, you just multiply. So the point is that if you have so if q of square root of a plus b of q is such an extension, then can multiply this then q of lambda a plus lambda b square root of q is such an extension as well. Such an extension as well. Well, for all lambda, well, maybe in q star. So you see that we get many so but now I hope that this this problem is finished, but do you have any questions? Everything is clear, crystal clear.
Just add that if there is such an extension, then there's then there's a series of such extensions for all lambda in invertibles.
Yes, there are. Yes, there are infinite.
And why does such an extension exist? We got that.
Yes, you're right. You're right. You're right.
We
Yeah.
got that if there exists one such an extension, then there is a series.
Yeah, you see, sorry, I'm sorry. Yes, you're right in the sense that it's not no, because so far it's not clear because so far we only know that that there are many solutions solutions for A and B. Yeah, so for a given Q we are looking for A and B such that this identity, well, this condition holds. And of course, you can always multiply A and B by something to get infinitely many solutions of the infinitely many pairs of A and B to satisfy this condition. But you're right in the sense that we have to check that. No, it's okay. I mean, it's we have. I think it's okay because yes. So we just have to check that this condition guarantees that this extension is exactly as we want. Yeah. So if yes, so let us come back to our argument. So what was the argument? The argument was that we consider such an extension. We consider such an extension, and it is definitely of degree 4. Yes. Is it? Are you sure?
Yes.
But maybe can it happen, for instance, that yeah, because yes, because why? By the way.
B is not equal to 0.
Yeah, and so.
And so we can just write down.
No. Wait. You see that, for instance, if let me give you an example why it is not completely trivial. Consider so well when Q is, for instance, Q is 2. Q is 2. Oh, by the way, I'm sorry, it's not true. Yeah, it's not true. It's not true. It's should be. It's not -1. Yeah. Because you see that P is also good. Because -1 is square modulo. Yeah. Okay. Yeah. So for instance, here, 3 plus 2 square root of 2 Is this of degree 4? Well, we can try to look at this polynomial. So it will be x square minus 3 square minus what? Minus 8. Yeah. Minus 8. Is that okay? X minus 8. This is x.
Нет, значит, четвертый степень. А там же здесь. А если взять не двойку, там что-нибудь побольше, чтобы отрицательное было, тогда не будешь. В смысле, чтобы корень из 3 минус n, корень из 2, просто в действительных числах не содержался. А это содержится расширение, очевидно. Положительное число. А если четвертая степень, то все да.
Well, I'm not sure. So. Okay, so what do you think of this? Is this so? What is the degree of this extension? No, I have a concrete example, and I want to know what is the degree of this field over here. So you see, well.
We can look at this polynomial model of different primes.
Okay.
And if it splits in factors of different degrees, I mean by one prime and by another prime, then it's irreducible.
Okay.
So if we look at this one model 2, we will get
It's
x plus y.
x plus 1 and fourth. Yeah, okay.
And modulo 3, we will not get x plus 1 in fourth power.
Okay, and
then it should be irreducible.
no.
No?
No, because you see that when you get splitting in linear terms, factors, then it gives you strictly nothing.
Okay.
If you could get 2 plus 2 and 1 plus 3, 2 plus 1 plus 3 and 2 plus 2, then yes. But I have some doubts. Yeah, so, but anyway, So just to double check what was going on. So first, what was the argument? The argument was that this is of degree 4, and then that it should be. So then yeah. So what was the argument? That it is of degree 4. Then it's Galois group. So what is its Galois group? Its Galois group should not be contained in even permutations. Yeah. It is of course. It should be. Yes, it is not contained. What could be the group? Yeah. So yes, it should be. Yes, it is not contained here, and yes, and we there is a unique. Yeah, so you see that so far we have not proved that that these triples, well, or these pairs A and B, satisfying this condition, give us an extension we're looking for. You see that. Because in principle, so what if, assuming that this is of degree 4, even assuming that this is of degree 4, we have to check that.
But we know now that discriminant is not square.
Yeah. So it means, but you see that what are the options for this group? For the Galois group. So it may be Z mod 4, but it may be, you see that it may be, what are transitive? So the question is, what are transitive subgroups? Transitive subgroups of the symmetric group on 4 elements. But not in A form. Well, of course, you have this cyclic permutation. What else do you have? You have well, the maybe. Of the symmetric group on 4 elements of S4, not in the alternative group of on the subgroup in the subgroup of even permutations. Well, so what are they? So they are, well, say 1, 2, 3, 4. So this cyclic group, yeah. What else? Maybe the Silov subgroup, Silov 2 subgroup. This you can do you have maybe those generated by 1, 2, 3, 4 and 1, 2, 3, 4, something like this. No, does it work? I'm not sure. Yeah, you see what happens when you apply this one. So you get 2, 1, 4, 3. Yeah, it's okay. Yeah, so this one. Maybe generated. Yeah, generated. And the whole symmetry group itself. So S4. You see that it should be. It should be divisible. Yes. So this the order should divide 24. So what are divisors of 24? 24. So divisors which are at least 4. Yeah. So this is 4. Yeah, so maybe yeah, you see, but even here you we have even here we have well, of course it doesn't look like I don't think we have the full symmetry group here, yeah, because well, for some trivial reasons, namely if this is of degree 4, then of course we have so we see that we have alpha, minus alpha, beta, and minus beta, and of course certain we don't have, for instance, we cannot permute. We don't have cycles of.
If we really have minus beta, I mean, if this can be a negative number under
square root. Why not?
Shows.
Why not? Sure. No, the only thing I want to say is that actually the only options are here. There are only 2 options because you see that if we have alpha minus alpha, beta minus beta, then we don't have cycles of length 3. We don't have elements of order 3, and therefore this is anyway a 2 subgroup. So it is either cyclic of order 4 or the whole seal of 2 subgroup. So the only option here is to so the only thing here we have to exclude this one. And but again, I'm coming back to my equation. What is the degree of this extension? Okay, maybe. Do you remember some school tasks like finding the complete square, completing I don't remember how it's called, completing the square, or how to solve quadratic equations? Yeah.
can check by hand all possible
Divisors of what?
of this polynomial, because we know all its roots.
Do you?
We built it to have roots. I mean, square root of.
Okay. All right. So you see, what is written here? What is x to the fourth minus 6 x square plus 1? So it is square of this, yeah? Minus what?
Minus 4x
Minus
square.
4x square, okay.
So it is x square minus 1 minus 2x.
Okay, yeah, so
Why is the polynomial of this alpha like that?
well, you just, because this is just 1 plus square root of 2. Well, of course you can forget this one. Yeah. So you see the problem.
But we, so we should look at all divisors in general situation.
Yeah, but in general, yes, but you see that actually the Galois group defined for any polynomial, even for irreducible one. Yeah. So it's maybe it's not a big problem. Or it is. I'm not sure. But the problem is yes, but the problem is rather that we get here we get a trivial extension. Yes, so that's the problem. But well, we can try to construct this extension explicitly. Yeah. So yeah. So once again, what was wrong here? What was wrong here? And why? And what will be? You see that even if this was, we just want to check what will be, what will happen if we still proceed the same way. Yeah. So if a plus b, can it happen that what was wrong here? So for instance here, that would, yeah, you see that actually this would give us, an even permutation, yeah, because it is, because alpha and beta are more or less the same, yeah, so they, the only non-trivial element changes the sign of both of them. Is that okay? No, it's not true. No, it's false. It is false because so the problem was that no, it was false. It was false. But anyway, this permutation was even, yeah, because it was two inversions, yeah. So it was excluded here. So the example was 3 plus 2 square root of 2, and here a square minus qb square was 1. So you see that it was excluded already at this point. So now let us check that this may not happen. So let us a prime plus b prime q square. What is this? This is a square plus b square q plus 2a prime b prime q. So what happens if we look at this? A square. So, well, actually, I'm sorry. We don't need to write that explicitly. So we can just write gamma, which is a prime plus b prime square root of q, and then what? Then if we consider gamma, yeah. So gamma. So suppose that a plus b square root of gamma is square root of q is certain square. Then this. What is this? This is just the product of this is so then a square minus b square q is the square of gamma times the conjugate. Yeah, so let me write this: a prime minus b prime square root of q square. Yeah, and in the brackets we have a rational number. So this is a prime square minus b prime square q square. So it's not. So this is excluded here. So it's not possible. But yes, and of course when we multiply by yeah, so that's how we get. Yeah, so now we have indeed a degree for extension. What have we checked? We checked that it contains square root of q. We wanted to contain the conjugate where this what was called beta somewhere. Well, maybe not on this. Yeah, it's here. This one. Beta is also here because alpha beta. Alpha beta is, we know that alpha beta is a multiple of square root of q. Yeah, and so original multiple, so it is there. And so it is, and this means that this is a Galois extension. So it is a Galois extension, then it is a Galois extension with a group either this one or this one. So how could we exclude this option? Can we do that? Or we can't? That's right. Yeah, it's a Galois extension. Yeah, that's right. Yeah, so we don't have such a problem. Okay, now have we finished or not completely? So what? So is it a Galois extension? Is it a Galois extension? Yeah, because yes, because beta is alpha beta is this element, and this element is already there because that's how we choose our A and B. Yeah. Yeah, it's a Galois extension. Yes, you're right. So it should be. Okay. So, do you agree that it is finished now? Because. All right. So. So we have. Okay, so maybe we can discuss some other exercises like. So what have we constructed so far? For instance, can you find the Galois group? Of such a field?
First of all, we should completely agree on everything.
Okay. Where? Here?
Well, this seems to be Z2 squared.
Why?
So that's the problem.
There is three possibilities.
No, but
Z2 squared is Z4 and the third is.
no. You see, there is one more. Maybe it's not a Galois extension.
Well.
element.
Mhm.
So this extension of degree 4.
Yes, okay. So it's x square minus 2 square minus 2 is, yeah, it's okay. It is, yes, it is Eisenstein of degree 4. But is it Galois?
Может напомнить, пожалуйста, Eisenstein?
So it means that it is a monic or with invertible first coefficients, leading coefficients, and all other coefficients is divisible by some prime, but the constant term is not divisible by p square. So it is
So
Well,
the first coefficient is invertible.
Everything is-
all others are, except the constant, are divisible by p, and the constant is not divisible by p prime.
p square. Mhm. Okay,
So to check, is it Galois? To check is square root of 2 minus square root of 2 is contained in our thing.
yes, that's right. Yeah, so it's square root of. So
So
is it there?
we conclude that the product of this one and another one is square root of 2. And we know that square root is definitely less.
Nice. Yeah. So it is alpha square minus 2 is square root of 2. Yeah. And yeah, and so it also contains square root of 2 over alpha, which is beta. Yeah. Okay. So yes, so it is a Galois extension.
So we should check is it containing contains even permutations. So the discriminant is not square. So it then contains in A4 and
Actually, that's it, because if it is Galois, it is of degree 4. So then, discriminant is not square. By the way, is it? It is 2, yeah? Oh, well, 2 times 2. Well, 2 times some. Yeah, but you see that it is modulo squares. Discriminant is alpha beta. Yeah, so it is it is a square minus qb square modulo the rest. Yeah? And so it is. Yeah, so it is not there, and that's it, because so it is. So the Galois group is Z mod 4. Okay, but actually you see that this is precisely what we did before. But maybe, just we can try to continue a little bit, like square root of 2 plus square root of 2 plus square root of 2. Is it? What can you say about this? Are you sure? So you want to continue this? Yeah. Square minus 2 square minus 2. Yeah, okay, it is of degree 8, yeah, because it is also, of course, I understand, yeah, so it's 4 minus 2, it's...
so we get that discriminant is not square, and...
Why?
But
How do you know this?
It's so we know that our previous extension is sub-extension of this one.
Yes.
So we can say that the whole group is some semi-direct product.
Wait. Is it a Galois, first of all?
So it's Galois because it contains the root. I mean the only one non-obvious root is square root of 2 minus I mean the square root of all.
Yeah. So.
I mean the big square root 2 minus square root.
Like this? Like this? Okay. But you see that we want, so here, yeah, so it is irreducible. It is irreducible. Well, of course, you can say that, well, maybe delta. So gamma delta is, what is gamma delta? It is square root of 4 minus 2 minus plus square root of 2, yeah? So this is square root of 2 minus square root of 2. And we know that it is there, yeah? All right, so you have delta here, but what else could we have? We need also eta. We need 2 plus square root of 2 minus square root of
Well, we already have
y.
Надо опять. Опять еще такое. 4.
Ну, видимо, перемножить. Ну, видимо, мы хотим сначала, чтобы у нас с минусами только было. Потому что тогда мы
Ничего,
можем...
опять запряженный множить.
Ну, смотри, мы хотим сначала, чтобы было все с минусами.
Ладно, если немножко на другой.
Maybe well, maybe it's too complicated, yeah, because so does it look like that? Yeah, so yeah, maybe it's too complicated. Actually, it doesn't look like Galois extension, yeah?
Maybe if we suppose that it is Galois and look at the possible groups, we can say something that they does not act transitively.
Mm-hmm.
I mean, Z modulo 4 semi-direct product with Z modulo 2 should be transitive in S8.
Yeah, but well, we can try to. You see that this is a quadratic extension, yeah. This is I mean this one. This one is quadratic extension. Let's denote this by by sigma. So this is an element sent gamma to its opposite. So this is the fixed field, you mean that if it is a Galois extension, then there should be a subgroup of automorphisms fixing some intermediate subfield, like I don't know, like square root of 2 or something, because we don't have any other subfields. Or even Q, yeah? So that's, where could we send Q?
Сейчас, подожди, я просто не уж- может,
Что?
я просто, неправда, что для полупрямого произведения вот этих вот групп
Каких?
всегда верно, ну, что если мы предполагаем, что это расширение Галуа, тогда группа должна быть Z4 полупрямо на Z2, может просто тогда в этом в S8
No. If it is, you see that if this is a Galois extension, so it is a group of degree 4, or degree the group of order 8.
Yes.
So the options for the group of it may be Z mod 8 and also it may be it contains Z mod 4 here as a, of course, as a sorry, as a quotient. No, as a quotient. It contains yeah. So it is modulo this sigma. It is Z mod 4. And it is Z mod 4, and this is a normal subgroup. Is it? Is it a normal subgroup? Yes, it is normal. It is a normal. This sigma generates a normal subgroup because this is a Galois extension of. This is a normal extension of Q. Yeah. So modulo subgroup of order 2. It is Z mod 4. Yeah, so maybe we should write this. C is a normal subgroup, and G modulo this subgroup is Z mod 4. What does this mean? This means that either G is, of course, it may be cyclic. And what else? If it is not cyclic, then it has, as you say, it should be a semi-direct product or just a direct product.
Yes.
So next Z mod 2. So Z mod 2 acts on
It is the integral group.
yeah, and or just direct product. Okay. Yes. Oh, I'm sorry. It is. You see that. Is it possible that? You see that this group should be normal. So.
Z mod 4 should act on Z mod 2.
Yeah, because you see that if we can try to lift, so we have this isomorphism, so we can lift a generator here. Well, let's say psi. We can lift it to some psi tilde in G, and so psi can be either of order 8 or well, sorry, of order of order 8. It may be of order 8 of order 4. So order 8 gives us this case. Order 4 gives us either. Wait, if yes, if it is a order 4, it is a normal subgroup. Yeah, so it is. We can find an element in the complement of this subgroup, but I'm not sure. But it seems that this is not possible because this should be a normal subgroup. But here we don't. I don't see any normal subgroup of order 2. And outside of this normal subgroup, you see? So C, you see that here we have also C. C, so we have a subgroup generated by xi tilde, and C is not there. This means that yeah. So this means that this is just a direct product. Direct product because so this is generated by C and this is generated by xi tilde. And they should commute. They should commute, I think. No. We have to check that this is a direct product. Why should they commute? Because C is normal, so C xi tilde sigma is equal to sigma xi. Why? Because xi sigma inverse is, you see that this is a normal subgroup. So this should be a C. And this means they commute.
Okay, so
all right. So
So we have xi tilde isn't xi tilde minus 1.
yes, you see that
Еще раз, как это работает, то, что внизу написано?
you see that we have here an involution sending gamma to its opposite because it's a quadratic extension. So we can, of course, we have such an involution. And on the other hand, the resulting fixed field is Galois extension of Q, and this means that the subgroup generated by sigma is normal. What does it mean that it is normal? It means that when we conjugate elements of this subgroup, we get to this subgroup again.
And how did we get to psi?
it doesn't matter, any element here.
Mm-hmm.
Any element here, doesn't matter, we just take arbitrary. There are only two elements in this subgroup, so, and of course, if we take a non-trivial, non-identity element, then we also get a non-identity element.
And wait, how did it get to psi when we had sigma? I still don't understand
No.
this transition.
No, so far, yeah, you see, we just to check that, yeah. Well, psi, you see that the quotient, it is a normal subgroup, and quotient by this normal subgroup is the Galois group of this field.
Mm-hmm.
And we know that the Galois group of this field is cyclic.
This is C, not, or sigma, or what is this?
This one,
No, G modulo.
this one,
Yes. Is it C or sigma?
this is C. This is this in. Oh, sorry, thank you. Yeah, sigma.
Mm-hmm.
Yes,
So,
thank you.
And
Mhm.
then, what is psi?
Psi,
Is
some
element?
yeah, you take a generator of this quotient
Mm-hmm.
and call it psi.
So psi is some element.
A generator, yeah, some generator of this quotient.
Some generator of this quotient. Okay. Or
Mhm.
then.
Then you lift it, and the options are either it generates G, so G is cyclic, or it does not.
So under here it was written as psi sigma psi minus 1.
Yes, psi inverse.
Alright, I thought it's like psi included in.
Sorry. Sorry, I forgot that it was sigma and not C.
Alright, so then psi is some is the generator of Z mod 4. Then it was normal and
Well, just lift it, yeah. So as so here is also sigma.
yeah. So and we get psi tilde. So we had psi and then we got psi tilde.
Yeah, we just lift it, and maybe we don't really need to assume that it is not here. Yes, I mean if it is not, you see that the options are that psi tilde generates G. This is this case, and if it is not, if it does not generate. Yes, and if it does not generate generate G, then we take we look at sigma, and sigma, and you see that if sigma is not in yes, sigma and sigma and psi tilde have to generate the whole group G, because it is by
unless we get that this cannot be Z mod 2
semi-direct product. Yes,
semi-direct product
yes,
of,
yes. So if
because they are independent.
yes, so if sigma is not contained in subgroup generated by this psi tilde, then they just generate the group of order 8 just as a direct product of these two groups. Okay. Now now we have to so we have to check these two options. So can we do that? For instance, so far you see, so far we have sigma, yeah. This is definitely well defined, and can we, for instance, can we try to produce another automorphism like this one? So, for instance, can we send gamma to this, well, to something like this? Does it induce an automorphism of this field?
Я не очень понимаю, что мы делаем. В смысле, не должен же. Ну, сейчас. В смысле, другого.
You see that how could you check that this is a Galois extension? You have to find an option is to find an automorphism sending a primitive element to another generator, another primitive element. Yeah, so of course this is so gamma generates this field, and it is sufficient to check that this is
So can factor the minimal polynomial of our generator and then look at the orbits.
So we agree that this element contains is contained in our field. Yeah. So it's by the way. So for or we can try to find the fixed subfield, assuming that it is well defined. Yeah.
Maybe we should look at the minimal polynomial
Of what?
of this element to which we sent.
This one?
Yes. I mean over some bigger field, maybe with square root.
You mean over this one? Yeah.
Yes.
Okay.
And see if it also roots of the same polynomial as gamma.
Okay, let's see. So okay, yeah. So what is
Maybe not this one. Maybe just q with square root of 2.
okay? Yeah, but then the minimal polynomial over this one is well, I'm not completely sure, but you have to probably just x square minus 2 square x2 square minus 2 square minus 2 minus square root of 2.
And how did we get
Just
Well, just you raise this to the square. You square this, subtract 2,
so
and square again
it's a polynomial of
of the same
Q
element gamma over
Q
this.
over Q of square root.
yeah. So
Yes.
if we look at the minimal polynomial over the bigger one field, then they will different because
They will be, yeah. So so this is gamma, and you mean what do you want? You mean this one, yeah?
yes.
Eta. So it will be x square minus 2 square minus 2 plus square root of 2, yeah? Okay.
So so the yes, so the Galois yes, so the Galois group of our maximal extension over this one cannot send one, I mean gamma to eta, because they are roots of different
Okay.
polynomials.
Yeah. So they are, of course, they are also Eisenstein here. So because yes, they are Eisenstein. There.
Yes. Yes. Yes.
Yes, they are.
Right. The constant is not divisible
Yeah,
by
by
2.
No, by square root. By 2, yes. By 2, yeah.
All other coefficients are divisible. So
Divisible, yeah.
divisible, so it seems to be.
Yes, it's.
So they have different polynomials, and thus these are different extensions.
I mean, there is no automorphism that send gamma to eta.
But wait, but you see that there is no wonder, because no wonder there is no such automorphism, because you assume that square root of 2 is fixed. But of course you. But we can try to look at. Oh, you don't think will give us anything good. Hmm.
Что у нас с дискриминантом? Мы же дискриминант посчитаем.
Ну хорошо. Yeah, so discriminant, but what discriminant? So you mean that it may be square? So yes, if it is so, yeah. So far our options are Z mod 8. By the way, can this group be transitive?
I hope not, but
No, well, just a second. 1, 2, 3, 4. Yes, it can be. It can be because so you see that you have cyclic. So you have two columns, and you have cyclic permutations in well, simultaneous cyclic permutations in columns, and one permutation of this type. Yeah. So in principle, it is possible. So is it? Yes, it is. It is transitive. Okay. Okay. So you want to calculate the discriminant, yeah? So what do we have? Gamma, delta, eta. What else? Gamma, delta, eta. Well, it will be. You see that it will be quite. Oh, you.
Может, вольфрам. Говорю, параллель вольфрам можно посчитать.
So you know how to calculate this determinant, the discriminant using
I hope
Wolfram.
it can. Просто число.
Вот для этого.
Ага,
Порядка 10 в 9.
класс.
Сейчас, пускай отвечает.
Да. Там очень интересно. Там получился вот такой дискриминант.
Ну да, сейчас мы узнаем.
Какое-то громадное число.
Это корень квадратный. А, это квадратный корень из него, да?
Это 2 в 31 степени.
Так это дискриминант, а корень квадратный из него.
Как 2 в 31
Это 2
степени
в 2 в
дискриминант, значит не квадрат.
Не квадрат, да?
Да.
Не квадрат. Yeah. So if it is not a square, then yeah. But wait, you see that is this? I think that you see that we can probably exclude this case, can we? If it is not a square. If it is not a square, then what is this group? Zima 2, yeah, so it's you see that sigma is even, yeah, because it is the product of 4 transpositions, yeah, and this cyclic permutation is also, sorry. Алло? Да? Да, да, привет. Нет. Нет. Ну, через... Ой. Да нет, ну, через какое-то время. Давай потом перезвоню. А что? Ну, я не помню, там ну, как бы, когда пара кончится, когда там...
Смотрите, у нас 2 пары, мы можем сейчас перерыв сделать, потому что у нас уже почти, у нас осталось 50 минут примерно.
А, осталось 50 минут где-то, через 50 минут.
Вот, мы можем сейчас сделать перерыв.
Ага, а что? Или что-то срочное? Угу, ладно.
У нас минут 50 осталось.
Ага. Ну хорошо. Yeah, so so this is yeah. Maybe the question is whether So what is so we know that sigma is even, and what about xi? Yeah. So everyone agree that sigma is even, yeah, or not? Not everyone.
Yes.
Sigma because so what is sigma? Sigma just changes sign of each exterior square root. Yeah. Wait. Maybe. Не обязательно, я? Не обязательно. Да, действительно, сейчас.
Если мы хотим, чтобы действовало транзитивно, то может и обязательно. Потому что там вроде как это должно быть произведение 4 транспозиций разных. То есть вроде как меньшим количеством мы не обойдемся.
Yeah, maybe we could try to look at this more geometrical. Yeah, maybe because it becomes too complicated. Yeah, so maybe we should think of this. What is this actually? What this could actually mean? Does this have some geometrical meaning? Yeah. What do? We what do you remember from school? I mean, like cosine of the half angle. What is cosine? Cosine of of theta over 2. What is this? Maybe twice cosine. It is 1/2 of.
Cosine squared.
1 plus cosine theta over 2, yeah? plus, you see that this is e to the,
Okay. Mhm.
so it is square, yeah? It is 1 plus 1. 1 plus 1. Well, something like this, yeah? So now what do we want? We want, so if you think of so what is square root of 2? Square root of 2 is
Cosine of P4.
yes, pi over 4. 4, sorry. So what is cosine cosine of pi over 8? Maybe twice cosine. It is twice square root of 1 plus square root of 2 over 2, yeah. Does it help? Not that much, yeah. Mhm. And well, this maybe this is not exactly what we want, yeah. Well, but still, let's try. Let's try it just to see what kind of numbers could we get. 1 plus 1 plus square root of 2 over 2 over 2. No, yeah, you see that this way we get don't get the same kind of numbers. Yeah, so the conclusion is that it is unlikely that this is a Galois extension because okay, well, let's see. Yeah, so we have to yeah, so well, if this is a Galois extension, then this should be an automorphism, yeah? Or not? This is
Мы еще не имеем по модулю простых братьев. Ну, в смысле, могли бы взять многочлен, брать по модулю простых, создать какие-то скоровые типы. И что не получится.
okay. Well, maybe we should skip this, yeah, because it turned out to be too complicated. Maybe we should do something more feasible. Okay, so just to so what we didn't define so far, maybe. So okay, this one we have defined here. We have checked. Yeah, so maybe we could. Can I ask you whether you can find some groups, some obvious? Well, maybe not that obvious, just to make sure that we solvable. Yeah. Okay, like something huge, like x to the 7, then x5 plus 15x plus 5. Yeah. So what is well, maybe not just maybe the question can be, is it solvable in radicals? Oh, well, of course, over the rational numbers. Ну, по крайней мере...
это же 7 будет, да?
7.
В смысле?
В смысле?
Группа подстановок 7 элементов.
Да.
Ну, Вольфрам дает гипотезу, что здесь 2 вещественных корня
Да.
всего. А если это так, то это и 7. Ну, мы это на прошлых занятиях когда-то доказывали.
Сейчас два невещественных. Или вещественных.
Блин, действительно.
Подождите, на 2 вещественных это выглядит странно.
Наоборот, он говорит, что Вольфрам говорит, что...
Нет, один вещественный. Я соврал, действительно, так не может быть.
Нет, почему-то оно...
У вас разный вольфрам, наверное.
Сейчас смотри, вот.
Ну, сейчас. x7 минус 10x5 плюс 15x.
Минус там. Блин.
Минус.
Мне он говорит, что 5 этих вещественных и...
5 вещественных. Нет, ну и все остальные. Ага. Yeah, okay, so... Yes.
Мне очень нравится, как он их показывает.
Какой-то корень вектора окрестности.
Ну, видимо, он имеет в виду, что там не все цифры после запятой. Yeah, so this Wolfram says that it is something like 1, 2, 3, 4, 5, yeah, something like this.
And 0 is between the third and the fourth.
It doesn't really matter. But actually, it's you see that. But how could you do this without
So
Wolfram?
we should take a derivative and
Yes,
see.
yes. So 7x 7 minus 50x 4 plus 15. And but still 1, 2, 3, 4. Yeah, 1, 2, 3, 4. But it's a cubic equation. y cube y square, and again we can take derivative
Мы его уже и решить можем в целом, вот правда.
cubic.
Да.
А, ну да,
Well.
конечно, у нас же...
Да, будет весело, да.
Well,
Да.
you can, yeah. Of course you can try to, but
Надо просто попытаться посчитать количество корней, это имеется в виду.
mhm.
Ну,
Нам надо два перепада, чтобы...
но нам, получается, нужно раз, два, три, 4 корня у этой штуки.
Нет, надо просто, чтобы корни производные вещественные были. То есть,
да. То есть нам нужно
есть
два
еще-
вещественных корня производной в игреках.
1, 2, 3, 4. Yeah, 1, 2, 3, 4 means and here 1, 2, 3, 4. It means that we have to have here. You see, they should be the point is that the roots here should be positive, but they are positive because
Вопрос. Если мы возьмем y заменим на y, то умножим на y куб. У нас же получится уравнение, у которого все корни это единица делить на корни исходного, так?
ну, если да, если
Ну
обращаете.
вот. Значит, тогда можем просто такую замену провести и решить относительно единицы делить на y. И, ну, просто чтобы свести ее к красивому виду за одно действие, а не вот как оно сейчас. Ну, в смысле, мы хотим свести к виду y куб плюс by, да, плюс by плюс c.
Maybe we should believe this Wolfram that there are five real roots of this polynomial, and therefore, so then the conclusion is that the Galois group is the full symmetric group. Yeah, so it's not solvable, but well, then
So the Galois group is not.
it is 7. Yeah.
It is S7.
Yes, it is because as we discussed, so it is because you see that it is a group containing an element of order containing the cyclic permutation of maximal length, and it has a
The transposition.
transposition. Can't find exercises. Oh, I lost something. Oh, yeah. Well, maybe I should, maybe next time we will discuss certain versions of this procedure. You see that so far we only use complex conjugation, but we can also use some other arguments, namely instead of complex conjugation we can use so how does this argument works? This argument works as follows. So we have a field K. We have its extension K. Well, actually completion with respect to the some valuation of some Archimedean field K, in our case it is Q, and completion R. And then our polynomial splits, so P over R splits as a product of linear terms x minus alpha I times Q some polynomial times a polynomial of degree 2, yeah, and that's the argument. But it's not important here that our field extension is R. Yeah, we can take any extension such that this happens, or even better, you can any extension you can take. In principle, so what we have discussed when we dealt with sorry. So here, we have to assume that our so it is we have to assume that there is an automorphism. Yes, there is an automorphism we extend this field to something else, and then there is an automorphism of this field. First of all it splits, and so degree of Q is 2, and there is an automorphism. There exists automorphism. Sorry, maybe we just can say that this is a splitting field of Q, yeah? So, splitting field of Q. L is splitting field of Q. Okay, and then the only yes, and I think that's it. That's it, because is that enough to conclude that the group is the full symmetric? So maybe I should stress that P is a prime. Here we remove these conditions. So P over K is irreducible. So this is over this extension. That's it. I think then we can conclude that.
Мы еще использовали то, что сопряжение Q на месте оставляет здесь.
You see that it's not a problem because our field is embedded into this. Then the Galois group of P is the full symmetric group. So again, what is the argument? The argument that the Galois group acts transitively on the roots of this polynomial, say in L, and there are p of them, and it contains transposition, yeah, namely transposition of the roots of the polynomial q. Okay. Yeah, so that's so in principle, instead of and maybe one more remark is that if we instead of real completion, if we deal with periodic completion, then actually we just have to check that our polynomial splits into this form only modulo p. What is p? No, it's different p. Well, modulo L, yeah. So, well, maybe I don't have example an example with me, but I'll try to find it next time. Yeah. So. Yeah, maybe we should do this something else. What? But yeah, maybe next time we'll try to find this. I'm sorry. Okay. Yeah, and maybe coming back to what we have discussed last time. So. We I'm sorry, but where is the yeah, maybe we can try to play a little bit with expressing something in well, or if you're not afraid, expressing something in radicals. Okay. Well, then не надо, да? Ну ладно. Ну, я не знаю, там корень седьмой степени из единицы, например. Лучше не надо, да? Хорошо. Так, тогда сейчас я что-то хотел сказать. Черт, я, кажется, все забыл. Там у меня где-то это было, видимо, в другом или здесь. Вот. Ну хорошо, давайте тогда. Maybe instead of сейчас я хотел. Окей. Ладно. Это тоже что-то не то. Well, then maybe we should try to play a little bit with decomposition subgroups and some examples with Piezo series. Okay, maybe, well, maybe remove this one. So first of all, well, let me recall you that so if we have a field K, we consider its well, some, you can think of this as a colimit or some union of formal Laurent series in fractional powers of x. So these are Piezo series. So series. You see that we consider Piezo series. So and so the claim is that we will discuss maybe not today, maybe later. So that if K, let us call this simply K of x1, if K is of characteristic 0, and it is algebraically closed, then for instance the field of complex numbers, then the field of Piezo series is algebraically closed as well. Okay, but may I ask you a question? So, is it true? Is the same true for, say, for a field of characteristic 0, of positive characteristic? Characteristic of K is positive. So, can it be algebraically closed? But let me just give you a hint how, or maybe you can say it yourself. How could you prove this in principle that this field is algebraically closed? So, for instance, if you take x to the n plus a minus 1 small x minus 1 plus a of x. Yeah, so how could you prove that how could you start to prove that this equation has a solution?
Еще раз, как эту штуку все устроено?
To give,
То есть получается там все дробные степени.
well, not really. All you see that any, maybe I should write this. So any, maybe I should write this as a set. Yeah. So it is the set of sums an x to the n over big N. So you see that big N for each series you have
And the smaller n is
from something to plus infinity, from n naught to infinity, and big N is fixed for each series. Well, it's not fixed, but I mean, there exists some n such that each collection of powers comes from integers divided by n, big N. And of course you can add them, multiply, and even invert any non-zero series like this, because it's like a usual Lorentz series, but in slightly different variable.
So I think first of all we should go to usual formal series.
Yeah, so we can assume that. Yeah, so we may assume that all these coefficients are just usual Lorentz series. Okay.
So I want to go further to just formal power series, not Lorentz, to somehow apply Hensel lemma.
Wait, but then this means that you pass. You see that here there are some negative powers of x. Yeah, so you have to get rid of them somehow. Or of course you can, yes, you can say that you have an extra coefficient here, and then of course you are right then that you can consider power series, and they are coprime, yeah, and they are coprime, if you wish. Do you? Ну не жалко, да. Окей.
Теперь надо как-то, значит, по модулю x написал, у нас будет алгебраически замкнутое поле. Поэтому решение найдется.
Wait,
Только
so-
чтобы это
So you say that modulo small x, modulo small x,
we have an equation with coefficients in algebraic that goes to
yes, yes, but something I don't like. Something I don't like something in this step because so let's try to see mod x. Mod x, you see, so what may happen? It may happen that modulo x, for instance, you have x then plus a1 and 1x plus 1 is 0, yeah?
Okay. So we need some coefficients which are not free and which has which doesn't zero modulo x.
Yeah, so
Maybe modulo x, this all is just some constant.
yeah, so we get 1 is equal to 0, and it doesn't have any solution, unfortunately. Yeah, so even k is algebraically closed. Yeah, so so the problem is so the first thing we have to think about is that what is the order of our root? What could be the order of our root? So, for instance, here, of course, we have to look at the orders of the summands. So what? So let us denote this by v. So v. So v is well, we can say. So v is just the order x to q. So order. Oh, valuation, I don't know. Order of 0. Order of 0 of valuation. So it sends x to the n. It is a homomorphism. It sends x to the n to n. Well, maybe q to stress that our powers are rational. Okay, and then we have to look at each summand. So v of a I plus I, and then we have to think what could be this order. Yeah, so I times v of x. V of x. This is what we have to choose. So we want it to be 0. So how could we choose it? We take so we want to choose this.
Where did the grade x come from?
Sorry.
We have
We
the bigger x. So we have small
no.
x
So far
and the bigger x, and do they coincide or?
No, big X. We see that's the we are looking for the for a root of this polynomial.
So this is some polynomial
Yeah.
in
Over this Puget series field, and we want to find the solution of this equation, and we think we try to find what could be the order of this of a root of this polynomial, so as Vladislav suggested, we can try to reduce this modular small x, but the problem is that it may happen that everything is divisible by x except the constant term, which gives raises some problem. So we have to modify this. Modify means that we let us put here instead of some alpha, so we want to find some alpha such that
Мы можем подобрать множитель, чтобы раздвинуть.
yes, that's the point. So before reducing, we have to shift a little bit our x, our coefficients, so that they will be non-zero. Yeah. So okay.
Ну и сейчас здесь, а если у свободного члена минимальная valuation, то есть мы хотим как бы на минимальный сдвинуть, чтобы.
Yes, but you see that alpha may be negative.
Yes, but then we will have Lorentz series as coefficient.
No. You see, it's. I mean, it's. Then you can shift on the whole equation. You see that you can. For instance, here, if this coefficient vanishes.
Yes, I mean we can shift to the left only on the length of the minimal valuation of our coefficients.
Oh, okay. So what do you propose? So to.
I mean that there can be some problem if the minimal valuation is on alpha null.
Okay. So if yeah, so suppose that v of a naught is minimal. Yeah, so it is strictly less than strictly.
Strictly. If not strictly,
I for I greater than 0. Okay, then so
I mean, otherwise it's easy to shift.
And it's smaller or include?
strictly small. Okay, so what?
Сейчас. Там знак просто меньше.
Строго меньше. Yeah. So, but it's not. I mean, it's not a problem because you can easily. If it is strictly small, well, you can assume that it is 0, yeah, because.
We can.
You can assume that because you just divide everything by this. If this is minimal, then you can divide by this, yeah.
Okay, so.
So we divide A by AO.
Yes, by a naught, yes.
We can just.
If it is minimal, of course you can divide by it. But if you don't like that it is minimal, you can change it because you you can look at all these. Well, you can, for instance, you can. You see that you can take. So maybe you should consider rather v of ai over I. Yeah. So this one, this ratio, and then you can subtract. If you want, you can add or subtract certain rational number, so that this will become 0 or even negative. So by changing x, you can move somewhere. Yeah. So for instance, you can. Well, of course, dependent. You can look at so which. So if this is.
So if we change in x, the free coefficient is not changing, so we can just shift to the let's of the minimal.
Yeah.
Yes, the minimal valuation, and the rest will be coefficient with 0 valuation.
Yes. Yes. So this. Yes. So you can assume that. Yeah. So this by no. Yeah. So you fix. So let alpha be equal to what? To minimal. Yeah. Minimal.
Yeah, because they're all strictly positive. Because we
So
assume the
yes, minus minimum v at ai over I. Yeah. And then we get yeah. So where I is strictly positive. Yeah. Between 1 and m. N. Yeah. Okay. All right. And then what does this give? This gives that there is j between 1 and n such that v of aj is 0.
Смотрите, я потерялся. Почему мы делим на i?
Чё? Почему делим? Потому что мы делаем замену. У нас because so the question, why should we divide by I? So the point is that we replace x by what? By x to the alpha, well, x prime. Let us denote this again by x to the I. So and this is ai x to the alpha I xi, and the valuation of this ai x alpha I is what is this? This is I times times what? Times v of alpha v of ai plus alpha. Okay. we just you see that this is the valuation of AI plus alpha I. So we can divide everything by I, and we get this. Okay. Yeah. Yeah. Okay. Yes. But yeah. So we stop here. But just well, not to finish, but just to give a hint what is going on. We by this shift we reduce equation to the following to the equation where one of these coefficients with some non-zero power of x is
Becomes 0.
is well not zero but non-zero modulo x modulo small x, yeah, so invertible.
So we can find roots.
Yeah, so then we get then after reducing modulo small x, we get a polynomial, a non-constant polynomial, which is important. Yeah, and a non-constant polynomial has a root, and then we can iterate this procedure. Well, not iterate, but well, yes. Oh, but carefully, because there will be a...
Тут производные характеристики нуля, все нормально.
Uh,
Мы можем предположить, что они приводили? В целом.
yes, of course, we can assume that this is irreducible because if it is not, then we can split and look at its irreducible factor.
Ну вот, тогда он правильный, характеристики нуля, все хорошо.
Yeah, it's yeah, probably you're right, but yeah, probably you're right. Okay. Yeah, and so try to see what is wrong with in characteristic P. You see that so far we haven't used any.
For separability. I mean, only for separability of irreducible polynomial.
No, it's not a problem. Already for separable. No. I think even no for actually for there is no problem for purely inseparable extensions. The problem is for separable extensions, as far as I understand.